Assalamu alaikum everyone. Welcome to the course of Digital Signal Processing. Today we will continue chapter number 4, lecture number 8, sampling of continuous time signals. So in previous lectures we have stated that how we can sample the signal in time domain and frequency domain, and how we can reconstruct the discrete signal back into the time domain. Today we will talk about discrete time signal processing of continuous time signal. So let's get started. So as you can see in figure 4.11, this is the discrete time processing of continuous time signals block diagram. Here we have C to D and we have D to C. Now this block diagram represents a large class of system. The only thing that we need to do is to change the sampling rate and the discrete time system. So for example, you have a continuous time signal and you want to low pass filter that continuous time signal. So what you have to do, you have to select the appropriate sampling time in C to D, and you have to use the appropriate discrete time system. For example, in the case of low pass filtering, we need to have discrete time system to be low pass filter. If you want to have a high pass system, like you want to do high pass filtering, we need to have high pass filter in place of discrete time system. Likewise, in D to C, the only thing that we can change is sampling time. So here we are calling it continuous time signals because we have continuous time input, we have continuous time output. Only the discrete time system is discrete. So let's get into the mathematics of this diagram. In previous slide, the overall system was continuous time system because the input was continuous and the output was continuous. We were converting those inputs into discrete, then we were processing it in discrete, and then finally we were using D to C reconstruction system to convert back into continuous time. So in previous section we have seen that in C to D, the C to D converter produces a discrete time signal. As you can see that the relationship is given in 4.29, that x of n is equal to xc and t. So this is a sampling process in time domain. Its equivalent in frequency domain is the Fourier transform of x of n is x e raised power j omega. Then we have the spectrum, this 4.30 equation. You must have seen that equation, that we find the spectrum of xc of t and then we discretize it. So the summation is because of the copies of spectrum, and this 2 pi k is the multiple of sampling frequency and 1/2 is the scaled of those copies. So the Fourier transform of equation 4.29 is x e raised power j omega is equal to 1/t summation k is equal to minus infinity to infinity x e j omega, and we have replaced the capital omega with omega by t because this is the discrete time Fourier transform, and omega s by 2 pi k divided by t. So this is C to D, and when we come to the D to C portion, we know that in D to C, the D to C converter creates a continuous time output signal. So we know that in time domain, whenever we have to create a continuous time signal, we multiply our discrete signal with sinc function. So you can see that summation n is equal to minus infinity to infinity y of n is the discrete signal, and sine pi t minus nt divided by t divided by pi t minus nt divided by t is the sinc function. So that is the impulse response of the reconstruction filter. That was a low pass filter. So ultimately what we get, yr of t. Yr of t is the reconstruction. First in equation 4.29 we did sampling, then we represent the sampling in frequency domain, that is in 4.30. Then we are talking about reconstruction, that is D to C converter in equation 4.31. So let's move on to next slide. So in equation 4.32, the equation 4.32 is exactly what we have seen in 4.31. The 4.31 equation was of D to C in time domain. So if I take the Fourier transform of yr of t, then its corresponding Fourier transform will be y e raised power j omega. but because our reconstruction, this is our reconstruction filter, this is our reconstruction filter. So the Fourier transform of y e raised power j omega is y e raised power j omega t, because this is continuous, so continuous Fourier transform. So the output will be y r j omega, which is equal to y r of t. If I take the Fourier transform of this will be y r j omega, and this is the output of discrete system. So we have a discrete system. So if I draw it, here we have x of n, here we have y of n. So y of n, we can, the y of n Fourier transform will be y e raised power j omega. So if I represent it in continuous, so this become y e raised power j omega t. So what we are doing, we are applying a reconstruction filter on the output of discrete system. So you have seen the block diagram, we have continuous time input, we discretize it, and then we pass it to the system. Okay, after passing through the system, we get this output y e raised power j omega, or the Fourier, which is the Fourier transform of y of n. Once we have the discrete output, we want to reconstruct, we want to convert into continuous. So for that we are applying a filter. This is the output of the system, and now this is the output of the D to C. Okay, so we know that the reconstruction filter only applies a gain of t. So whatever our discrete output was, we will multiply t with this, and then this reconstruction filter has the limit omega s by 2, which is equal to pi by t. So we will have only one copy. So the output of this will be omega less than pi by t. So whatever value that comes in between the omega range will be the output. Okay, so here we can have, now let us relate the output sequence y of n to the input sequence x of n, or equivalently their Fourier transform y e raised power j omega and x e raised power j omega. Now this is very interesting example. This will help you understand what we are actually doing here. So if we have x of n input and we have y of n output and we have their corresponding Fourier transform, now in place of discrete time system, if we say that the discrete time system is 1, it means its identity, whatever is at the input is coming at the output. So we can define the system like this. So the system is doing nothing, it's just passing the input and the output is coming. This is the case that we have stated in detail already. We know that if xc of t has a band limited Fourier transform, so we have seen that if xc of t, we have seen the examples of cos, we have seen the example of that triangular function. So both of these are band limited. So its Fourier transform, the Fourier transform will be 0. For example, if this is the band limited signal, so its Fourier transform is 0 beyond these. So Fourier transform is 0 for omega greater than pi by t. It means that this is just a baseband signal that is just around the 0. Okay, and if the discrete system in figure 4.11 is the identity system, then what will happen? So y of n is equal to x of n is equal to xc of nt. It means that we just need to sample the continuous time signal. It means that we have to sample this xc of t, we will get x of n, and then because the system is identity, our y of n will be equal to the input, then the output will be yr of t is equal to xc of t. Then after reconstruction, our output will be equal to the input. Recall that in proving this result, we utilize the frequency domain representation of the continuous time and discrete time signals, since the key concept of aliasing is most easily understood in frequency domain. So we know that we can easily understand the concept of aliasing in frequency domain. So that's why we have used this condition of spectrum copying, that your spectrum must need to be 0 beyond the half of the sampling frequency. So let's move on to next slide and have a look at a example that will be easier for you to understand this whole process. So just keep in mind that block diagram that you have continuous time signal, you have C to D, you have discrete time system, you have D to C, and finally you have continuous time signal. So in this slide we will talk about the discrete time systems. So we have seen that in our main block diagram, that is figure 4.11, we have continuous C to D converter, we have discrete time system, and then we have D to C. So here we are talking about LTI, discrete time system, where actual processing takes place. Okay, so we know that in discrete, this is the Fourier transform of the input, this is the frequency response of the system, so we get the output of the system. So if we have this block diagram, here we have, before this we have C to D, after that we have D to C. We are not talking about this, we are talking about this discrete time system. Here we have x of n and here we have y of n. Their corresponding, this, the Fourier transform of this is x e raised power j omega, and the Fourier transform of this is y e raised power j omega. And this system is h of n in time domain or h e raised power j omega in frequency domain. So if I multiply this h e raised power j omega with this x e raised power j omega, I will get y e raised power j omega. Okay. Now, once I have this y e raised power j omega, what I need to apply on this in order to get the output D to C? So this is just same equation. Just replace this omega with omega t, and then this is D to C. We know that in D to C we have a reconstruction filter, so we are applying a D to C converter here. And finally, after D to C we have y r of t, or if I talk about Fourier transform, we have y r j omega. Okay, so this is y r j omega is this the system, the input, and that's the reconstruction filter. And we know that what reconstruction filter does. Reconstruction filter only apply the gain of t and selects only the baseband signal or the copy at 0. So here you can see that after this, if xc of j omega is 0 for omega greater than pi by t, then this ideal low pass filter, reconstruction filter, cancels the factor 1 by t. We know that there is a factor of 1 by t whenever we sample continuous time signal. So what will happen after all this, after this reconstruction, we will get the original spectrum and the response of the discrete system. So we are not worrying about C to D, we are not worrying about the discrete time system, we are not worrying about the D to C. All this nails down to what? All this nails down to discrete time system. This is discrete time system, and then the Fourier transform of the input. The Fourier transform of the input. So the output will be equal to the original spectrum multiplying with response of the discrete time system in this limit, because beyond this limit output will be 0. So we can read this line now. Thus, if xc j omega is band limited and sampling rate is above Nyquist, we know that we must need to have sampling rate above Nyquist, otherwise we cannot say this will happen because copies will mix up. Then the output is related to the input. So this is the Fourier transform of the input. This is the effective response. Effective response means the response of D to C, the response of discrete time system, and C to D. When we solve all these, we get this effective response. Okay, so this effective response, is equal to what? If I just convert it into discrete, this will become e raised power j omega t. So how we can get this effective response? This effective response is basically this. We just ignore this, and we say effective response is the response of the discrete time system. I can clear that thing later on with the help of example, Let's move on to next slide. So here you have an example of ideal continuous time low pass filtering using discrete time low pass filter. So this is ideal low pass discrete time filter. You can see that we have copies. So we have amplitude of 1 between minus omega c and omega c, and then this filter repeats its response at 2 pi, 4 pi, 6 pi, minus 2 pi, minus 4 pi, and so on. Now effective responses means converting that discrete low pass filter into continuous. So how we can change this discrete into continuous? We simply divide this by t, because we know that omega is equal to capital Omega into t. So we need to get this omega, so we simply divide our small omega with t. So here you see the axis change to this and the frequency is changed to this. So the difference between discrete frequency response and continuous frequency response is they are just the time scaled version. So frequency response of discrete time system corresponding effective response. So this is the effective response for a band limited input. So whenever we have a band limited input, we will have a response like this, and we can represent this mathematically. H effective j omega 1. It is 1 between the limits omega is less than omega c by t. So we have mod, so we can have both the values, positive and negative. And when omega becomes greater than this, we have 0. Okay, so omega c here represent cutoff frequency. Okay, so let's move on to next slide. So this is an example of system shown in figure 4.11. This is the spectrum of the continuous time signal. So it means that we have a signal xc of t whose Fourier transform looks like this, and this is obviously a band limited signal because beyond omega n it is 0. Now what we do after generating periodic impulse train, we convolve this xc j omega with periodic impulse train and we get these copies. Okay, we get copy at 0, we get copy at omega s, we get copy at minus omega s, and this is half of the sampling. So you see we are getting the copies. So this signal is omega, this is xs j omega, it means sampled impulses, and we can also write it like this, x e raised for j omega t, it doesn't matter. Okay, so now we have, this is the output of C to D, this is the output of the C to D. Okay, now after C to D we have a discrete time system. So this is the system here, this is the system. You see it applies on all the copies here, here and here. Now what does this filter do? It just removes the upper frequencies. So you can see here we have this signal and now we are removing its upper frequencies. So it's known that omega c, this small omega c, is less than this omega n. So obviously one thing more importantly, that we need to apply the filter. This filter is in discrete, so we have to convert this into discrete. So how we can convert this upper graph into discrete? By simply multiplying it with t. So if we multiply it with t, the 2 pi by t converts to 2 pi, this capital omega converts to small omega, this point pi by t converts to pi, here we have pi, here we have minus pi, not shown but this is, and this if we multiply this with t, it becomes minus 2 pi, and obviously this point was omega n, if we multiply it with t, this will become omega nt minus omega nt. So one step is missing here, but you can easily understand that this is continuous. We have to convert into x e raised for j omega. So for that we have to multiply our x's with t. So now we have x's multiplied t, we can apply this filter, and this is discrete time filter. So what we are doing, we are multiplying x e raised power j omega with h e raised power j omega, and we are getting the output y e raised power j omega. So this is the output. So you can see we have copies at 0, at 2 pi, minus 2 pi, and now the upper frequencies are removed. We do not have something like this. The upper frequencies are removed. Okay. So this was the output of C to D. This was the output of LTS system. Now this output will be fed to the this is the output of the D to C. So here we are applying the reconstruction filter. You can see this is HR j omega. So because the reconstruction filter is continuous, we have to convert this small omega to capital omega. So how we can convert? We can divide we can do this. We have to get this capital omega, so we need to divide this by t. So divide by t, and this divide by t, this divide by t, and then this filter has a cutoff of minus pi by t to pi by t, and we know that pi by t is equal to half of the sampling, and the filter gain is t. So we have converted this to y e raised power j omega. Then we are applying the reconstruction filter. Okay, so once you apply the reconstruction filter, this copy will be removed, this copy will be removed, we are only left with this. So what happens? We have done processing of the continuous time signal. Now let's make things easier. We know that this signal is a band limited signal. And when the signal is band limited and Nyquist criteria is satisfied, we don't need to do all these things. What we can do, we can directly apply H effective. We can apply directly this response. So what is H effective? If you go back to previous slide, H effective is just like this: omega c by t minus. So if I apply on this, I will get this output. So you can go back, you can go back and you can check how we can apply. So directly applying H effective filter, we know that H effective filter is low pass here. So just applying this on the first copy, we can directly get this. So this is the purpose, that we do not need to do all these steps as long as we know that the input signal is band limited and this Nyquist criteria is satisfied. So you can read the caption and hopefully you got this. Let's move on to next slide. So as we know that both the discrete time and continuous time systems are interchangeable. If we have one, we can find out the other. So the example 4.5 states discrete time implementation of ideal continuous time band limited differentiator. So we will use continuous time differentiator to create discrete time differentiator. So we know that if we have a continuous time signal, you can see, and I derivate it, it becomes yc of t. So this is the input, this is the output, and this is the function that is derivative. And we know that the corresponding frequency response means if I pass this xc of t, if I have xc of t and I take the Fourier transform of this and then I pass through this system, it's just like taking the derivative. I will show you in next slide how this is the derivative. So anyways, at this point we know that the frequency response is xc j omega. That is the frequency response of a continuous system. So we know that when the signal is band limited, we do not need to specify that the frequency response is this. We just need to specify in some interval. So we know that the frequency response will be j omega. This is the same thing, but within this limit it should be less than pi by t. So we know that we can draw this. You can draw the magnitude of this and phase of this. This is an imaginary value, so you just need to ignore. We know that magnitude is equal to square of real plus square of imaginary whole under root. So the only values unknown is pi. So if you put the value of pi starting from 0 the value of omega starting from 0 and go up to the limit pi by t. So this final point will be pi by t, and likewise for negative 0 and go to minus pi by t, this will be this. So this is the magnitude response, and for phase you have to take the tangent inverse of imaginary divided by real. Okay, so for positive value it will be positive phase, that is pi by 2, and for negative it will be minus pi by 2. Okay, because tangent inverse of 0 is 90. Okay, tangent inverse of infinity is 90 and minus infinity is minus 90. So we have the effective response of a continuous time system, we have its effective response of the phase response. Now we are converting that effective response to discrete time system. So you know what we have to do, we just need to multiply this with t. So it's just like scaling. So we have scaled this, and this figure and this figure is same, but in discrete we have periodicity. So whatever we have at 0, it will repeat itself at 2 pi, and then it will keep on doing, and it will repeat again at 4 pi. So we have periodicity in magnitude as well as we have periodicity in phase. Okay, so now this is the frequency response of the discrete time system. So we have j omega, we have replaced omega with omega by t. Okay, so now if you take the inverse Fourier transform, and we know, everybody knows the formula of inverse Fourier transform, that is 1 by 2 pi integration from minus pi to pi, that is the maximum frequency, and the function is j omega by t e raised power j omega t d omega. So if you integrate it, you will get this thing. So here you are shown about, or you are told about the discrete time implementation of ideal continuous time band limiter. Okay, so this system, what does this system do? This just takes the derivative of the input signal. Okay, so let's move on to next slide and see how this differentiator works. So now we have a system that is band limited differentiator, and we have the input that is cos. So everybody knows, if I take the derivative of the cos, it becomes minus sine omega naught, it will become minus sine omega naught t, and then the derivative of the augment, it will become omega naught. So here you can see the output is minus sine omega naught t into omega naught. So we have to show it with the help of sampling and all these C to D and D to C conversions. So we know that we know that the discrete version of cos omega naught t is cos omega naught n, where omega naught is equal to cos omega naught is equal to capital omega naught t, and the limit is less than pi. So what we have to do, first we have to take the Fourier transform of this. So the Fourier transform of this is periodically repeated copies. Everybody knows the Fourier transform of cos omega naught t is cos omega naught n is 1 by t summation pi delta of omega minus omega naught plus pi delta of omega minus omega naught. Do not get confused yourself with this k omega s. This is just because of the copies. You know that first we have this is the spectrum of the cos. Okay, now once we convolve this with periodic impulse train, we get many copies. So this is just that saying. Okay, this is when we xc j omega convolve with s j omega, we get this thing. Okay, and this is the discrete version, please keep it in mind. So what we have done here so far, we have directly written the sampled form of cos in frequency domain, and if we focus on the baseband frequencies, there is the only first copy that is at 0. So we just ignore this and we just ignore this. We have, and this summation will obviously be of no use when we are not using k. So this will be the spectrum. Okay, one will be at, this will be at minus omega naught, this will be at omega naught with the amplitude of pi by t. Now this is the input. Just keep in mind, we have just sampled it, we have not passed it to the system. What is our system? Our system is a differentiator. So now it is still in continuous form. It is still in continuous form because we have this omega. So we have to replace this with small omega. So we know that there is a property of impulse which I have already shown you. When you replace this, when we replace this capital omega, okay, what we have to do, we have to multiply, this will happen. We know that capital omega is equal to omega by t. So when we have delta omega by t, this is equal to t delta of omega. Okay, so what we have done here, we have multiplied with t, so t will get cancelled. We have pi delta of omega minus omega naught plus pi delta of omega plus omega naught, and the range was previously less than pi by t, so we have multiplied with t, so the range is now pi. Obviously this response is periodic and is repeat itself with a period of 2 pi by t. Here it repeated the period of 2 pi, here it repeats the period of 2 pi by t. Now this is the discrete input. Now we have the system. This is the discrete system. We apply this input. So if you remember the frequency response of the previous system, there was differentiator was j omega by t. So we are just multiplying this with input. It means that we are passing our input through this system. So we are doing it mathematically here. So once you pass this input from this system, after some simplification, we get this. Okay, now what we have to do, this is still discrete. What we have to do, we have to pass this through reconstruction filter. So whatever the output was, our output was y e raised power j omega. So we replace first omega into capital omega because reconstruction is always in continuous domain. And this is our reconstruction filter, and this is our final output. We know that what reconstruction filter does. Reconstruction filter does, it just accept one copy and provide a gain of t. So this is gain of t, and obviously we have only one copy because here we have ignored all the copies. Here we have ignored all the copies, we just have one copy here. So this filter will only select one copy and apply the gain of t on this signal. So we have this equation, replace this small omega with capital omega t, capital omega t, t. Now solving this, once you solve this, you will have 1 by t. You will have 1 by t. Now solving these, now further solving this, if you further solve this, this t gets cancelled with this t, and this omega naught by t becomes omega naught. Likewise, this t gets cancelled with t outside, and this omega naught by t becomes omega naught. Okay, so here's our final equation. Now everybody knows the impulse inverse Fourier transform. If I take the inverse Fourier transform, the inverse Fourier transform of this impulse and the inverse Fourier transform of this impulse is 1 by 2 e raised power minus j omega naught t, 1 by 2 e raised power j omega naught t, and then the scaling of j omega naught, j omega naught. So this is equivalent to, everybody knows that, 1 by 2 j e raised power j omega naught t minus 1 by 2 j e raised power j omega naught t. This is equal to sine omega naught t. So here we have j in numerator, So multiply and divide this equation by j. So you will solve this and the ultimate result will be minus omega naught sine omega naught t, which is the derivative of cos. So what we have done here, we have taken the Fourier transform of the input signal, that was cos. We pass it through the differentiator system, we use the frequency response of the differentiator system, and then finally we reconstructed it and we have verified that our output is minus omega naught sine omega naught t. So this is the overall system that we have implemented. Let's move on to next slide. Now this is very important thing, impulse invariant. So the only thing that you need to remember here, I will directly move on to equation 4.51, but before that, if you look at this figure A and figure B, this whole dotted system is what? This is continuous time system. So the overall response of this system is equivalent to continuous time system, which is equal to effective response. That is the important thing that you need to remember. And here we are saying that the frequency response of the discrete system. If you know this frequency response of the discrete time system, you just need to convert it into continuous. Okay, because this overall system is continuous time LTS system, and this is the equivalent system of band limited input. So we know that if we look at equation 4.50, we know that the response of the system will be 0 beyond this limit, because after this limit for band limited the response should be 0. So by looking at this 4.4 this equation and looking at this 4.50 equation, if we compare this, we see that if I take the inverse of h e raised power j omega will be h of n, and the inverse of this will be t h c n t. This is known as the impulse invariance version, because this is response is in discrete domain, this is in continuous domain, or the sample we can say. So equation 4 point, this discrete time system is said to be impulse invariance version of the continuous time. So discrete time will be impulse invariant. Why we are saying impulse invariant? Because of this t. Now how we can prove that thing? So if you consider this equation and take out the Fourier transform of 4.52, we know that the discrete Fourier transform in frequency domain is h e raised power j omega 1 by t, and then the copies of this hc and t. So the copies are hc j omega by t minus 2 pi by t. This is all in discrete. Okay. Now if I just consider one copy, I don't need to consider this, because now I have put the limit. So only first copy summation will be gone, and this will become 1 by t hc j omega t. Now this is in discrete. Just take out the inverse. If I take the inverse of this, it will become h of n, and then I take the inverse of this. If I take the inverse of this, this will become hc n t. Now here we have 1 by t. Here we have 1 by t. So if you compare this equation, if you compare these two equations, so you will see there is a difference of t here. So what if I multiply t here? This t gets cancelled with t, so we will have no scaling in frequency domain. So that's why we have to put t here. Okay, so this is called the discrete time system is said to be impulse invariant. So only thing that you need to remember, the relationship between continuous impulse response and discrete impulse response is one is scaled. Okay, so discrete time impulse response is a scaled version of continuous time impulse response. And how we got to know that thing? From initially from this equation and this. If I compare these two, we see that the Fourier transform of this will be h of n, the Fourier transform of this will be hc n t with t multiplying. Okay, so one this equation 4.49 and 4.51. We started out and we have seen that if we have this thing, their Fourier transform will be this, and then for one copy this will be this, and if I take the inverse, I must need to have t here. I must need to have t here, otherwise this t will not be cancelled. Okay, otherwise we will have 1 by t here. Okay, so we must need to cancel this t. So that's why this is the impulse invariant version. So let's move on to our last slide of today's lecture. So now here we are just doing a simple example, a discrete time low pass filter. So we have a discrete time low pass filter that is obtained by impulse invariant method. So we have the continuous filter here HCJ omega, 1 when omega is less than omega c, and 0 when this is wrong, this should be greater than or equal to omega c. So we take out the inverse of this. The inverse of this is, we know that this is a square function in frequency domain. Its inverse will be sinc function. So everybody knows the formula of this. Its inverse will be this. Now the point is how to find out h of n. How to find h of n. So once we have this impulse response, we can replace this small t with nt and we can multiply it with t. So after solving we get t sine omega c nt divided by pi nt. So we know that capital omega c into t is small omega c divided by pi n. Okay, because this t gets cancelled with this t. So now we have, initially we have continuous impulse response, we have obtained the discrete impulse response. Now we can represent the frequency response of the discrete time system, which is 1 over the interval this and 0 beyond this. Okay, which is identical to hcj omega by t. Okay, so hc of j omega is hcj omega is equal to hc j omega by t. So the only thing that is shown here that you are provided with the continuous time impulse frequency response. So we have obtained the impulse response, then using the impulse invariant property we have obtained the discrete time impulse response, and then we have taken the inverse Fourier transform to show you the frequency response. Okay, so that's it for today. Hope you got it. If you have any questions, you can leave me a comment. Thank you. Bye.